Hello everyone and welcome. Today we're diving into the world of digital logic design by tackling a very familiar challenge, controlling a coffee machine. My name is TEIK, my teammate is WONG and XIANG. This circuit acts as the brain of our coffee machine, ensuring it only starts brewing when it's safe and notifying the user immediately if something is wrong. Our system has 4 key inputs representing all the necessary checks. A. The cup present sensor. Is there a mug ready to catch the coffee? If yes, it will output 1. B. The water level sensor. Is there enough water in the tank? If yes, it will output 1. And C. The coffee bean sensor. Are the grounds or bean are loaded? If again yes, it will output 1. And D is the start button. If the user press the start button, it will output 1. For the output part, we have 2 outputs to control the machine. X, the brew enable signal. This turns on only when all 4 conditions A, B, C and D are met. It's the ultimate safety logs. And Y, the error indicator. This turns on if the start button D is pressed but one or more of the other condition A, B or C is missing. Let's see how this translates into our quarter schematics. For the brew enable X, we use a single 4 input AND gate connected directly to A, B, C and D, simple and efficient. For the error indicator Y, we implemented the more complex expression. First, we use 3 NOT gates, instance 3, instance 4, instance 5 to invert A, B and C. Second, these inverted signals are fed into a 3 input OR gate, instance 2. And finally, the output of this OR gate is combined with the start button D using an AND gate, instance 6, to produce the final Y output. This circuit accurately implements our error conditions. The waveform simulation is the final step to verify our design. As you can see, brew enable X is only high when A, B, C and D are simultaneously high, for example, at the end of the simulation interval. On the other hand, error indicator Y is high whenever D is pressed but any of the required inputs A, B or C are low. Notice how Y is immediately activated whenever D goes high unless all other inputs are already high. This analysis confirms that our logic circuit correctly meets all the safety and operational requirements of the coffee machine control system. Next, we move to a critical concept in digital design, NAND gate. Let's see how our circuit is restructured. For the brew enable X, which is a 4 input AND function, we applied De Morgan's theorem. We replaced the AND gate with one 4 input NAND gate, NAND 4, followed by another NAND gate, NAND 2, with its inputs tied together and act as an inverter. This demonstrates how an AND function is efficiently created using only NAND gate. And for the error indicator Y is similarly rebuilt entirely with 3 input A, B, C NAND gates and combine this 3 input NAND gate with D input with another NAND gate and then connect to another NAND gate that acts as an inverter. Finally, we run the simulation for this NAND only design. Notice how the resulting waveform is functionally identical to our basic gate design. The brew enable X only goes high when all 4 inputs are high, and the error indicator Y correctly activated whenever the start button is pressed without a cup, water or beans. This successful verification proves that our NAND implementation is a robust and efficient hardware equivalent of our original logic. To conclude our project, we successfully translated the operational requirements of a common household appliance into pure digital logic. We achieved a working design in 2 key ways. First, by implementing the logic using basic gates, and second, by demonstrating circuit efficiency with an equivalent design using only the NAND gate. This project provided hands-on experience in using Quarters 2 for design, synthesis, and verification. Thank you.